So what is a simple frequency distribution table? It's a situation where each data value in the given data is represented against the number of times that that data value is appearing. And this number of times that the variable is appearing in the data, we usually call it the frequency. So in our case, our variable was age, measured in years. And now we want to find out if I have an age of 54, for example, in my data, how many times does that age appear in the data? The number of occurrences. In this case, the frequency defined, we count from the data, we can see 3 times the value of 54. So 3 is the figure we call the frequency. 55 observed only once, 56 the same, and 60 you can see observed 2 times. These variables are the number of times to which each of the data value corresponding here has appeared in the data. We call it the frequency. Now, if, for example, you have formed such a simple distribution, how then do you come up with the mean of the distribution? Let's find out. I will baptize my age, which is measured in years, as the X value. And then I'll baptize the frequency as F. And to find the mean of this distribution, I will construct another column where I'll multiply F by the corresponding X value, the age. Okay. For example, what is 54 times 3? What is 55 times 1? 56 times 1? All the way down until you're able to exhaust these data variables. And there down you find the sum. The sum of the frequency times the corresponding data value. This will give us a certain value here, which for now, let's assume we have already found. There's a figure there. So our mean, whichever we were calling the X bar, the mean equals to the X bar is given by the formula class. You have found your f of x, and for each you have taken to be summed to the next variable, okay? In that column, you have different variables. After you multiply the column x with the corresponding f, the frequency, there down you get the frequency times the corresponding variable, the sum of those results. And now you come and divide by, you go back to the column F, the frequency column, you find the total. Of course, you'll get a result here. In our case, there were 11 employees, so you come and divide by that summation F. The figure that you get is called the mean of your distribution. Just a simple distribution where you just count the number of observations to which a data value has been observed in the data. And so you get the mean of that distribution. Are we together, class? Before we move on to another way of forming the distribution, I would like to mention about the model variable. You can see there is this column frequency. You just highlight the one that is the highest frequency. The value corresponding with that highest frequency, this value of 54 is the one we call the model value. I repeat, in this distribution, we have the column we are calling the frequency column. The value that corresponds with that highest frequency in statistics, that is what we defined as the model value. So in our case here, our age of 54 years becomes the model value or the model age in this particular distribution. It said, in case you want to get the median in this kind of a distribution, you must first of all write all these data variables with how many times they are appearing. The one that will lie at the center, you'll have it as your median variable. So you are going back from the distribution into a set of data, arranging the figures in ascending order, to which that lies at the center, you'll call it the median variable of the distribution. I want to introduce the term called the standard deviation. Standard deviation is one of the measures of dispersion, which has got a very big relation to the mean of the distribution. How do we determine the standard deviation? Standard deviation, normally abbreviated as sigma, Greek letter, or delta actually, is computed as we require to find the square root of the sum of the frequencies, which you'll have squared the data variable as you multiply by the corresponding frequency. For each data variable, you square, then you multiply by the corresponding frequency. You divide this one by the sum of all the data variables in terms of how many times they are occurring, in other words, the number of observations. Then you minus, take the sum of the frequency multiplied by the corresponding data variable, divide by the sum of the frequencies. How many observations do you have there? Yeah? And remember this part, you require to square it. That gives us the standard deviation. So what do we need in our table? In our table, we need to add one more column known as f of x squared. Some people prefer to you square your x and then you multiply by the corresponding frequency. Whichever the way you want, it will still work for you. You may square the f, or rather the x first, you multiply by the corresponding frequency, or you can work with the two together. You square the value of 54 here, then you multiply by the corresponding frequency of 3. You square the value of 55 here, you multiply by the corresponding frequency of 1. And you do that until the end. Therefore, there down you'll get a total known as the sum of the frequency times the corresponding x squared. So you'll come up with the value here. You square your x, each of the data values to be squared, multiply by the corresponding frequency, and you'll have a total. Once you do that, you'll be able to find what is the standard deviation for your data that you're trying to deal with. Okay. I'm trying to be on the video, but if I find my internet is not okay, I'll be off. There's one of us. I know she really needs to see what I'm saying. Yeah? She's called Diana. Kindly support her in all ways, especially those who are doing banking. And I think I had mentioned about Diana in our class. So mean and the standard deviation, as you can see, they are really related. That if you have the frequency and there's a column known as x, first of all, you multiply the frequency by the column x for each of the data variable observed. There down we get a total. We must have known the sum of the frequencies or the total number of observations. This is also called the sample size, yeah? Once you get that, you'll be able to find the mean. And now you can see when you're getting the standard deviation, this value we have here on our bracket is exactly our mean. So if you're working in order, you should be able to get the correct value of the standard deviation. But let's not forget that on the standard deviation, first of all, you're squaring your data value, like the age of 54, and you will multiply this one by the corresponding frequency for each until you exhaust the data. And there you come and use the formula and the correct formula, yeah, to find the standard deviation. A point to note is that if I want to find the variance of my distribution, and we make sure during our free time, this data is already in our Moodle, in our document, we make sure that we find out what is the standard deviation upon these figures there. As you can see, I've not computed those values. The variance, I was saying, has a big relationship with the standard deviation, the variance of the distribution, which is usually given by what? Variance equals 2 class standard deviation squared. The standard deviation, you just square this. Deviation, sorry. The standard deviation. You square the whole of this. You square the whole of this so that you're able to come up with the variance. That means, in short, the variance of any distribution is equals to sigma squared. Hope that is clear. Now, what's the need of us computing the standard deviation? Let me take you back a little bit. I introduced a subheading called measures of central tendencies. We also call this one averages. Averages normally talks about the location, like among the data variables, what is that we can say it's on average, the mean of the distribution. Like we can also ask ourselves which value divides the distribution into two equal halves. In other words, which one is at the midway of the distribution? And again, we were also asking among the data variable, which one is appearing with the highest frequency? In other words, it's at the peak of the distribution. So they normally talk about the location, where is this and that within that particular data. The measures of location, also called averages, also called the measures of central tendencies. Now, the measures of dispersion, a good example, the standard deviation, talks about the spread of the data variables. And the moment you compute the standard deviation, it should guide you, for example, to decide on how far or how close are the data variables. I repeat, standard deviation falls under the category of what we call the measures of dispersion in statistics. And measures of dispersion normally talks about the way the spread of the data values is in a particular data. Such a way, the spread may be those data values are so close to each other. If you find the standard deviation is small, then you'll find the data figures are very close to each other. A good example, when you be computing the standard deviation upon this data, I would expect that whatever you're going to get here will be very small, because when you look at the figures of 54 all the way to 60, those figures, they are very close to each other. And my expectation is that the standard deviation should be guiding me on the spread that those figures were close to each other, that is with a smaller value of the standard deviation. In case the data values are far, far away from each other, like maybe we had an age of 2 years, another one is 50 years, another one is 100 years, those ages are so far away from each other. Our expectation would be that the standard deviation we are going to compute here will be actually a big value. So when the standard deviation is small, it means data points are so close to each other. And when the standard deviation is large, it tells us that the data values are far apart, or rather the spread is very wide in that data. Now, when you compute the standard deviation, you can be able to relate it to the mean of the distribution by computing what we call CLAS, the coefficient of variation, abbreviated as the CV. The coefficient of variation is again one of the measures of dispersion, which is computed as CLAS, the standard deviation, divided by the mean of the distribution, and I'm hoping you're writing divided by the mean of the distribution, which is given by X bar. The mean of the distribution, we are abbreviating it as X bar, and then we multiply this one by 100. Standard deviation divided by X bar, we multiply that ratio by 100. Meaning, if you are asked to compute the coefficient of variation, your variable should be reading a figure of percentages, 30%, 20%, and not anything negative. It should always be existing as a positive variable. And at no point should you compute a coefficient of variation that is actually greater than 100%. Sigma all over X bar times 100. What is the need of us computing the coefficient of variation? And then B, if the coefficient of variation is a figure that lies between 0 and 20%, anywhere between 0 and 20%, between 0 and 20%, this means that your data values are very close to each other. And the comment is that there exists what we call a low variation. These are low variation among the data variables, meaning they are so close to each other. And a good example, when you'll be computing the CV for this data, because I want you to complete, once you get the standard deviation and you have the X bar, the mean, you go ahead and find out where is your coefficient of variation to lie. In this case, the data values are so close to each other, you'd expect it to be between 0 and 20% thereabout, a low variation among the data values, to mean that those data values are actually having a very small difference in between. They are close to each other. Another scenario is you have computed the CV and then it is lying between 21% and 50%. It takes any value between that range. What are you going to make as your comment? This shows that your data variables are moderately variated. It's not that they are so close to each other, and again, they are not far away from each other. We say there exists a moderate variation among the data variables. A moderate variation among the data variables. Moderate. Which is a very good case actually, like in a business perspective. In a rare case, you'd find that you are stable in terms of maybe how you're generating your profits, because circumstances surrounding our performance in the business are actually determined by the events taking place in the same economy. For example, there could be you're experiencing high prices of the factory inputs. Other times, maybe the inputs, their prices are not too high. So with those variations, of course, you'd expect your profits generating, they'll also be fluctuating from one time to another. You end up having different profits variables from this month maybe to another. As you measure the level of your performance, you find that it is not stable. But again, you wouldn't expect all other. You don't, for example, hope for a case where you have a bumper harvest of 1 million pap as your profit, and then the following day you only have 2 shillings. then you stay another maybe 1 month, you end up having like 50 shares. You see, that is a very big difference. Yeah, it means it's something actually affecting your business at a particular period of time. There's a big effect that is coming, either positive or negative, of course, but it is affecting your business in a greater way. And that is not maybe a good business, because it shows that there are these big fluctuations. If you have a profit of $1 million and then the following day you go to 1, you never know whether you'll go to a negative 100 again. So at the end of the time, you have such fluctuations giving you a signal, and you find out what could be the issue behind you having such big fluctuations. So in case you compute your CV, most probably such big fluctuations will result to a CV value lying between 51% all the way to 100%. Any value in between this range would represent a case of a high variation, which is a signal to the business, for example, that things are not okay, you need to do something. A moderate variation and a low variation are good to rely upon. Like in a business angle, if you find, let's say you're making a profit of 2 shillings, tomorrow maybe you're making a profit of 3 shillings, another day you're making a profit of 1, that is okay, because there's some stability in that particular business. Even though there are low profits may be made, there's something that, for example, shows that this particular business at that level, it is actually stable. Of course, you'd expect to have high profits, but not to have risen abruptly, for example, such a way you don't actually have a way of telling about tomorrow. In that case, it may even lead you to have fear about you engaging into more activities in your business. So the CV guides on so many decision making in the management. For example, when you realize that there is such high variations among maybe the units that you're selling in the business, you may question why. Like you find you have produced, or let's say in the real estate industry, today so many clients stands up and you have sold like 20 projects to the clients. The idea of you being there, for example, the company taking over the projects, and now all of a sudden you have got 0 projects, yeah. And then all of a sudden, you see that shows some sense of a signal that something is not stable in this particular industry. So those are some of the things that you think of when you're trying to analyze your business in a particular industry. Okay. When I am computing, let's say, the standard deviation, which I've shown on how to go about it, it's very important to note that standard deviation can never turn to be negative. It will always read to be a positive value. I repeat, at no point should you be computing the standard deviation and then your result is reading a negative value. The same happened to the mean, yeah? Mean, as you can see, was relying upon the data variables here. So if I have an age of 54, an age of 60, and there is none of this which is actually negative, then it means I should be getting all values which are positive. Not unless now the values given here were negative. If they are negative, well and good, you'll get a mean of negative value. But if they are positive, something like age cannot take a negative value. Something like, let's say, number of people in a certain company cannot take a negative. There are some things in statistics, in your reasoning, you have to give a physically viable value, or rather a value that is actually realistic. Yeah, if you have to talk about the number of seats in a vehicle, they're supposed to be full seats. So when you're giving your figure and it's something that is going to exist, yeah, it has to be there, and therefore a positive value. Also, after you compute your standard deviation, at no point should it be more than the mean of the same distribution. Standard deviation should always be less than the mean of the distribution. So by the time you're computing your standard deviation, already you have an expectation if, let's say, you had already computed the mean of the same distribution. Okay. Okay. So I have indicated a subheading there on the screen, preparing a group frequency distribution table. But for us to do this, there are some terms that we require to familiarize ourselves with. And these terms, I would wish that you understand them before we start forming a group frequency distribution table. I've tried to put them in bold letters, as you can see, not bold, but big letters, sorry, with a big font, so that we are able to understand them, yeah? One is what we call a class, and a class is also called a group. Like what I was saying, I can put the values of 54 all the way to 57 in one category. That is what we call a class. An example, I may have some data to which I want to give it in terms of classes. So I may say a class of 20 to 30, maybe 30 to 40, 40 to something else. May have something like 20, say to 40 or to 30, maybe 30, maybe 30 to 40, maybe 40 to 50, and so on. Of course, it will be guided by how many data values you are representing and what is the smallest variable in the data and which one can you call the largest value in the same data. Assuming our values are ranging between somewhere 20 all the way to 50, they would fall in our three classes here. But assuming we had values lying between, let's say, 20 and maybe 100, of course, we would have continued defining our classes until we are able to see that we can cover the largest value in the data. I hope that one is clear. The way you choose your classes matters a lot because it will tell you how you're going out to do your calculations later. I have indicated a class of 20 to 30. I have also indicated a class of 30, 40, and I've also indicated a class of 40, 50. If you're keen on how I have labeled my classes, you'll observe that class, the value 30, it is appearing as my larger value in this first class. And I also repeat it in the next class. We normally call it in the adjacent class, okay? Value 40 here has been repeated to appear as the lower value in this other class. These types of classes are known as, usually known as the exclusive classes. I repeat, they are called exclusive classes. Why? Because the value 30, as you can see it, is not belonging to this particular first class. You will find it in the next adjacent upper class. I repeat, the value 30 has been excluded. It will not appear in the class of 2030. It is going to appear in the next adjacent upper class. The same happens here in our second class. The variable of 40 won't be appearing in the class of number 2, but it will be seen to appear or accommodated in the next adjacent upper class, that is class number 3. And the story will go on until maybe we'll have had the last class in our distribution. Now, I will come here and I count, given some data, I will count all the values between 20 and 30, 30 not included, they are going to fall in this class. So how many are they? They could be 10 or they could be 5. I register that 5 as to what we call the frequency. So here I have the class. I have the column I call the class. Of course, the class name is supposed to be defined by which is the variable that you are representing. If your variable is, for example, the age, so your class should be labeled as age, of course, in years. If the variable here is about the salaries of your workers, then it should be given out here and maybe measured in whichever units, pounds, dollars, shillings, and so on. I hope that one is clear. And then I've said you'll count all the variables which rise between 20 and 30, don't include 30, and then you say here the frequency, the number of observations that you see falling in that class. Let's assume there are 4, you come and give it 4. 4 is what we call a frequency. All the values lying between 30 and 40. 40 not to be included in this class, again you exclude it, you may count them, and let's say you have realized that this one are maybe 5. You exhaust the data depending on how large is the data, making sure that you record the figure that is the value that is appearing as your lower value in each and every class, and you also record the value that is appearing as the larger value in the data, or rather for each and every class. As you count how many data points are falling in that class, you are able to determine the frequency of each of the classes represented. Okay, now I want to compare this form of classification of the data with another one here. Let's assume the first class I say 20 to 29. Then the next class I say 30 to 39. The next class I come and say maybe 40 to 49. And I continuously do that until I'm able to exhaust the data. You can see now the value of 29 here has not been repeated in the next class. So when I am writing down my classes, these types of classes that I've used in this particular case, they are called inclusive classes. I repeat, these classes are called inclusive classes, where both the lower value in the class mentioned up to the largest value in that particular class, we normally call it the upper limit, they are going to be included in that class. So you'll count all the values ranging between 20 and 29, the two sides being inclusive in the class, and then you can assign a value. Let's assume here you have noticed that the frequency of the first class is maybe 3, the frequency of the next class maybe it's 7, the frequency of the last class, let's assume it's 6. So you keep on counting depending on how many data points falls in each of our classes. Now, why is it important to know whether you're using inclusive classes like these ones here, or you're using exclusive classes like these ones here? It is so important because in the calculation of what we call the mean, in the calculation of the median, in the calculation of the model value, that has to be directed by how you are defining the classes. Are they exclusive in nature or are they inclusive in nature? Very important to note that. Now, in the case of the class limits, you can see these figures which are defining the interval of the, or rather how wide is the class, okay? The value of 20 in my first class is called the lower limit in the class. The value of 30 in this class, it's called the upper limit. The value of 20, the lower limit, the value of 30, the upper limit. And each and every class do have what we call a lower limit as well as the upper limit. The same here, the value of 20, the lower limit, the value of 29, the upper limit. The value of 40 here, the lower limit, and the value of 49, the upper limit. I hope that one is okay when we have the classes which are called exclusive in nature, and when we have the classes which are called inclusive in nature, and that for each and every class, it has got two limits. The one on the lower end, we call it the lower limit. The one that is on the upper end, we call it the upper limit. Now, we want to separate the case of the exclusive classes from that of inclusive classes in the determination of what we call the class interval. If I want to use the class interval represented by small letter I for the classes which are exclusive in nature, you just take the upper limit, you minus the lower limit, as simple as that. The class interval in case of the exclusive classes is usually given by the difference between the upper limit and the lower limit. For example, the first class of 2030, okay, its class interval will be given by 30, we minus 20. And that gives us that in that class, it has an interval of 10 items. That is the class size, also known as the class width of that particular class. The interval for exclusive classes, the upper limit minus the lower limit. In case we have what we call the inclusive classes, assuming we have inclusive classes like these ones here, to find the correct class interval, we first of all get what we call the class boundaries. Class boundaries are usually the true mathematical variables that we normally use in the calculation of the median as well as the model variable in the construction of the histogram. Such boundaries are the ones that we go for. I repeat, when we are constructing the histogram, when we are computing the median, if we are computing the model variable, and also when we are drawing the ogive, usually we go for the class boundaries. They are the true mathematical values which tell us how or where is the boundary between any two adjacent classes. Where is a boundary between any two adjacent classes? And they are the figures which we'll use now to determine what we call the class interval in case we are talking about the classes which are inclusive in nature. I repeat, classes which are inclusive in nature, to find the correct class interval, we are required to first of all get the class boundaries. How then do I get the class boundary? Let me demonstrate this. I have a class of 20, maybe to 29. On the lower end, I'm going to subtract 0.9. So I'll end up having on the lower end 19.5 on the lower end. On the upper end, I'm going to add 0.5. So I'll end up having 29.5. You now consider to take these two boundaries. We want to get the interval. The interval of an inclusive class is given by the upper class boundary minus the lower class boundary. The upper class boundary minus the lower class boundary. So for us here, we'll have 29.5 and we minus 19.5. And the result that we are going to get, which is going to be 10, becomes our correct class interval. Maybe we want to use that for further analysis in our work. I repeat, for the class that we call inclusive in nature, find the upper class boundary, subtract the lower class boundary. That difference gives you the correct class interval, which you may use like when you're drawing the ogive, when you're drawing the histogram, when you are also computing the median, as well as the model variable of the distribution. I hope those terms are clear. Now, in our calculations, after we have formed our distribution, we may be interested on getting what we call the mean of the distribution. So how do we determine the mean of our distribution? How do we come up with the mean of the distribution? You cannot get the mean of the distribution if you don't have what we call the class midpoint. The class midpoint class is a value that lies at the midway in each and every class. Not for the whole distribution. Remember, for the whole distribution, we call it the median. But the midpoint is a value that will be at the center in each and every class. To come up with the class midpoint, assuming I have a class of, let's say, the class of 2030. To find the class midpoint, you'll take the upper limit, okay? You add it to the lower limit. That result you divide by 2, which gives you a midpoint of 25. And you'll do this for all the classes in your distribution. A good example is when you require to use the midpoint in the computation of the mean as well as the standard deviation of your data. To get the midpoint, I've said, take the upper class limit, add it to the lower class limit, and that sum you divide by 2 to find the value that is at the midway of that particular class. If you have an inclusive, this is a case of an exclusive class, the class of 2030. If you had an inclusive class, assuming 2029, again, you take your upper limit, you add it to the lower limit, and you divide that one by 2, which in this case will give us a value of 49 divided by 2. It will give us a value of 24.5. Whether inclusive or exclusive, the point is take your upper class limit, add it to the lower class limit. That sum you divide by 2, it will give you the class midpoint. Class boundaries, I've said, you must compute them in case your classes are of inclusive in nature. If they are exclusive, the limits and the boundaries are the same. They coincide and there is no need for you to compute them. I hope those terms are clear so that we can now move to the next stage of the computations and forming a group frequency distribution table. Resume. Now we have some data here, and these are the ages of some workers in a certain organization where I have indicated the variables in form of what we call a set of data. A set of data is where you keep on recording, like I have met these 50 workers. So for each I ask, what is your age? He give me on average, without maybe the months, assuming you are 26 years. Of course, most probably with a day or two after 26 years, but with the assumption that these are full years, okay? Then I move to another, he gives me or she gives me the age of 24 and I record, and I do so up to the age of 39. There are 50 data points. But now I want to use this to form a frequency distribution table that I can rely upon in the calculations of something like the mean, the standard deviation, the coefficient of variation, and so many other statistical variables that I may be interested in, or rather I may be interested on in maybe making a conclusion about a problem that I could be having in the organization. So I want us to know how we form the distribution first, and then from there we can continue with the calculations. The first, let me try to make this one bigger. Okay, hope that is better. So the first column is what we call class in general here. We call it class. But because there's something we want to represent in our data, we want to have the presentation of the age in years, we cannot call the first column here class. It has a name, and that is going to accommodate the age that is in our analysis. I repeat, age is our variable to be represented, and those ages are going to come in terms of groups. Those groups are the ones we call classes. But each and every class, we are representing age. And then on this other column, normally called the frequency, this is the column frequency, we are going to represent with the ages between this and that, how many employees are there. And that is what I want us to do together. From there, we guide on how maybe to do the calculations. So the first column here does represent the class. Of course, you give it a name. Ours is the age measured in years. And the next column is what we call the frequency. In our case, we have called it the number of employees. You can as well call it the number of workers in that organization whose age are falling between this and that. So this is a frequency, this is a class. You can opt to go for, of course, we have talked about two types of classes, the exclusive, and we also have the inclusive classes. The exclusive, all the exclusive, all the inclusive classes. In this particular question, I have asked, can we form a frequency distribution table? Can we form a frequency distribution table with the first class starting from the age of 5 to the age of 15? And I've asked, first choice, you choose the inclusive classes. Second choice, you go for the exclusive classes. You're starting from the age of 5, or rather the age of 15, sorry, maintaining an interval of 5 in between the lower value that you're going to have, and of course the upper value that you'll have in each and every class. So how do we do this? I'll start with the age of 15 as I am told, and I'm going to choose classes which are, I'll choose the classes which are inclusive. Let me start with inclusive classes. The inclusive classes. Okay, so we'll start with the age of 15, maintaining an interval of 5. And because my classes are inclusive, I'll go up to 19 years. So that when I move to the next class, I'll start from 19 to 20. I'll start from 20. My classes are inclusive. So I'll start with the value of 20 to 24. Then the next one, I'll start with 24 to 20, 25 to 29, 30 to 34. And keep on checking for me if I've gone up to the highest value. The highest value in my data is what? Perusing through this. 62.
Intervals.
Somebody is saying something? I think I'm not getting.
Intervals are 5.
The intervals are 5.
9 + 4. Yes.
Okay, let's finish up and then I'll explain. The next class we have 35 to 39. Next class we'll have 40 to 44. 45 to 49. 50 to 54. Have we exhausted the data? Not yet, we still need to move on. The highest is 60 as I can see from the data. So we go to 55 to 59. 60 to 64, which I suppose will have accommodated the highest, the 62. Now, somebody is asking, since the interval is 5, why are our classes like this? These classes, remember, are inclusive in nature, where we have chosen to go for classes maintaining an interval of 5, 5. Reason, the first class of 15 to 19 has accommodated 5 figures or 5 variables there, where, being our interval, remember the values of 15 and 19 are included in that category. These are inclusive classes. For inclusive classes, to find the correct class interval, what do? We take the upper boundary, we minus the lower boundary. So the boundary for the first class of 15 to 19, on the upper end, we add 0.5. So we'll have 19.5 as our upper boundary. On the lower end, we minus 0.5, so we'll have 14.5. And that difference gives us 5 data points as our class interval. The width of that class is 5. The same, if you are to move to the next class, the upper class boundary here would be 24.5. We minus the lower class boundary, subtracting 0.5 here would have 19.5. And again, it will give us an interval of 14 minus 9 is 5. I hope that one is clear. Now, I want us to peruse through this data and we mark the frequencies for each and every data point that we have. We count them as we make them to appear in the class where they're supposed to belong. I repeat, we go through this data. This is a set of data. We arrange it in what we call a group frequency distribution table by checking among the data variables where each of the data points would fall in our classes. So we start any age of 15 all the way to 19, 19 being inclusive, yeah? We are going to define them to fall in the first class. So we may go through the data. I'll be going through the data column-wise. So here we have got nothing to represent. The same here. Here, do we have anything to represent? Again, no. Next, we have the values of 18, 19, and another 19. How many are those? There are 3. The frequency equals to 3. 20 to 24. 24, remember, inclusive. We have 1, we have 2, this is the 23 here, 3, and another 23 here, 4, 25, 5, and I think we are done. So 5 data points there. 25 to 29, we have the 26, 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know if there's any other that we have left. I think we have picked all of them. So we record 9. And we'll do that until we are done with this data. So once we form the classes, we have chosen to be that they are inclusive in nature. We now go and tally the elements which falls in each of our classes here defined. We form a column known as the frequency. For you to now come up with a mean, you require these classes so that you are able to construct a column known as the midpoint. You want to get the mean, you first of all construct a column known as the midpoint, which I'm calling X. I'll baptize that one as X. So for the first class, 19 plus 20 plus 15, that gives us 34. Divide by 2, 17. 24 plus 20, that is 44. Divide by 2, giving us 22. 25, 29, that will give us what? 54. Divide by 2, 27. 30, 34, 64, 32 as the midway in that class. 37, 40, 44, 42, 45, 49, that is 94, 47, 50, 54, that is 102, 52. 55, 59, that is 100 and what? That is 114, 57. And lastly, 60, 64, that will give us a midpoint of 62. And you'll do that until the end. You will come and construct a column known as f of x, the frequency multiplied by the corresponding midpoint. For example, what is 3 by 17? 51. And you do that until you are able to exhaust all the data given. And now pale chini, we are getting the total, the summation f of x. Summation f of x, which will be given by a certain value here after you have multiplied your frequency by the corresponding the x, your midpoint. You go back to the column frequency and again you find the total, the summation f, your number of observations. In this case, there were 50. You'd expect that once you have, for example, completed the table, the total here for the column frequency will be equivalent to a 50. Once you have found your summation of the frequency multiplied by the corresponding midpoints, and you have also found the sum of the frequency, you can now come and compute your mean for the distribution. How do you do this? The mean, which is abbreviated as X bar, is going to be given by the summation of f of x. I think we had shown this area. And then we divide this one by the summation f. The summation of f of x, we divide by the total number of frequencies to give us the mean. But you cannot form the mean if you don't have the midpoints. And you cannot get the midpoints if you don't have the classes. And of course, taking note that you are getting the right frequencies of the classes that you have already represented. When you compute the mean with the data, you can as well get the standard deviation. What do we require? The column f multiplied by x squared. Your midpoint, you square it as you multiply by the corresponding frequency. Pale chini, again, you get the total. You find the total of the column we are calling the f of x squared. So you come here and you find the total. And now to find the standard deviation, the one we were calling sigma, to find the standard deviation, what do? You get the square root of, the formula actually remains as to what we had said earlier. You get the summation of the fx squared divided by the sum of frequencies, minus, of course, you bring your mean here, the summation f of x divided by the sum of the frequencies. And then the whole of these must be squared. And remember, once you have done your workings, you're getting everything under the square root. Hope that is clear. Number one, I have provided you with the data. You have gone ahead and constructed a frequency distribution table with some groups, with some classes. These classes, you have taken them to be inclusive in nature. You form that particular frequency distribution table, and upon it, you should be able to compute the mean as well as the standard deviation. For the other elements, like the median and the model variable, I will introduce those two later on. Now, so for the same data, we want to have a presentation of the classes which are exclusive in nature. And we have said our classes are going to represent the variable age measured in years. And for each of the class, we are going to record how many employees are having such an age, ranging, for example, between 15 and 20 years, or between 20, 25, and so on, until we exhaust the data points. So we have formed our classes with an interval of 5 in each class, starting with an age of 15 years. And as you can see, the interval is 5 because with the exclusive classes we had said, to find the correct class interval, just take the upper limit and you subtract the lower limit to give you a difference. For example, for the first class, 5. If you want to know the interval of the second class, you'd take the upper limit of 25 minus the lower limit of 20, again giving you an interval of 5. And you can confirm for every class we have here, we have a standard interval of 5 elements in each case. Now we go back to the data and we record the frequencies, the number of employees whose age is actually falling under each of our classes created here. We start the age of 15 all the way to 20 not included in this class. So the highest we can go in this class is up to 19. And we can mark those ages. We have the variables of 18, 19, and another 19. There are 3 of them. Now we include 20 in the next category if it's there, all the way to the ages of, remember 25 is not going to be accommodated in this class, but in the next class, okay? So the highest we can go is up to 24. And we can check those figures. We have 24 here, 1, 20, that is 2. We have 23, those are 3. 4, 5. I think we have counted all of them. So we would come here and indicate the frequency of 5. 25 to 30. We have 26, 1, 28, 2, 3, 4, 5, 6, 7 there, 8, and 9. So we represent that again, and you'll continuously do this until the end, so that you're able to form what we are calling a grouped frequency distribution table. A grouped frequency distribution table, where you form your classes, exclusive in nature. Exclusive means for every upper limit that you indicate in the class, don't include that value in the class, but you accommodate it in the next adjacent class. And you do so for all the classes until you have exhausted all the data values given in the data. Okay. If you want to compute the mean of the distribution, what do you require? The variable x given by the midpoint. So what is the midpoint in the first class? 20 plus 25. Don't ignore the value of 20 when you're getting the midpoint. The procedure is the upper limit plus the lower limit put together, you divide by 2. 20 plus 15, that is 35, divide by 2, 17.5. Next, 20, 25, that is 45, divide by 2, 42.5. No, 22, sorry, 22.5. 22.5. Okay, 25 plus 30, that is 55. Divide by 2, that will give us 27.5. Next, 30, 35, that is 65, giving us 32.5. And we'll do that until we have exhausted the data all the way to the end. If you want the mean now, you multiply the column frequency by the corresponding midpoint. There down we get the total, the summation f of x. We use the same formula into getting our mean. And the same, you can square your x, multiply by the corresponding frequency as you use the formula to get the standard deviation. And we had also said, if somebody wants to find what is the coefficient of variation, you just take the standard deviation, you divide this one by the mean of the distribution, and of course you express that ratio in percentages. So you multiply by 100. If the value CV lies between 0 and 20%, you'll comment that the ages of these workers were so close to each other. In other words, there is a low variation among the ages of the workers in this company. If you find you have a figure of between 51 and 100%, then the comment is that there's a high variation, or rather, the data values, the ages of the workers in this organization are far, far away from each other. But if you find your figure is lied between 21 to around 50%, a moderate variation, meaning the data points, the ages now, are neither too far away from each other nor too close to each other. There's a moderate variation among those data points. So that is how we form a frequency distribution table, which has been grouped actually, the one that is constituting classes, plus their corresponding frequencies. And of course, we may have inclusive classes as our choice, or the exclusive classes. Either way, remember, for the exclusive classes, the value that you put as your upper limit in each and every class is not supposed to appear in that class, but to be found in the next adjacent class. And for the inclusive classes, both the lower limit and the upper limit must be accompanied in that particular class. We stop there for today.